22.57 is a bit of a tricky problem. We're only doing parts A through C, so we can neatly cross out part D here. Okay. And we're looking at a non-uniform, but spherically symmetric, so we're going to think of Gaussian spheres here. Okay. And we have a charge density that changes. Okay. From when you're inside of a radius r, you're going to have this density, and when you're outside of it, you're going to have none. Okay. And there's a constant. I think they popped it down here in the problem just to make it so that it wasn't so messy inside the problem. Okay. The first thing they want us to do is to prove the total charge contained in the region is Q. Okay. Well, that's not as trivial as it seems, and they do that first to kind of make you prove that something is true. Okay. We're going to basically, you're going to think about it this way. What we're going to do is we're going to add up the amount of charge layer by layer. So if this is the region Q, and this is the radius R. Okay, that's R. I'll write it on the outside. What we're going to do is we're going to build up little layers. So we're going to start by adding up all the charge here, maybe. Yeah, and then adding up the next layer, and the next layer, and the next layer, and the next layer. And we're going to add them all together. Again, pardon my terrible circles. And we're going to add them all together until we find out what's the total charge in this thing. So, how do you know the amount in each layer, calculus-wise? Well, each layer, and I just drew one layer on the side, is a volume element. And the volume element has a thickness. It's hard to draw here for some reason. Okay. Has a thickness of dr. That's how thick it is. It's infinitesimally thin. Okay. And the amount to go around it. And again, this is a two-dimensional picture, but remember, it's a three-dimensional layer that we're actually drawing. So it's going to be 4 pi r squared. That's going to be our little bit of volume that we're going to multiply by. Okay. And we're going to have to integrate all the way across. So to find Planck, we're going to have to do the, we're going to have to take the expression 1 minus r over r and multiply it by that element. So it's going to be 4 pi r squared dr, because that's going to be our thickness. And we got to pop this guy in there, so let's erase this. And let's actually put the little expression they give us in here. So it's going to be 3q over pi r cubed, capital R cubed. Okay. And I did it just to emphasize that we can divide these out. And then we're going to factor everything that's not a, everything that's not a, that's not our variable out. So we're going to have 12q over capital R cubed on the outside here. And then I'm going to, that takes care of this, and this, and this. Okay. Then I'm going to distribute the r squared to the other terms and keep them underneath my integrand. Again, it's from 0 to r, because we're finding the entire sphere. Okay. And that's going to be r squared minus r cubed over r dr. Okay. All right. So, and again, it isn't really, it's a lot, it actually is pretty, when you look at the actual integral itself, it's not bad to integrate, just power rule will do it. So we'll start right here. So I'm going to keep the constant 12 over r cubed. Okay. I'm pointing out there's no epsilon naught or anything like that, because we're not even working with that. We're just working with Planck. Okay. Okay, just to prove something, 12q over epsilon naught. And it's going to be, we integrate it, it's going to be what? little r cubed over 3 minus little r to the 4th over 4r evaluated from 0 to r. Okay. And again, if we plug in 0, we're going to get 0. So it's going to be 12q over r cubed. That's going to be capital R cubed over 3 minus capital R to the 4th over 4r. You can see one of these is going to divide out right away. We're going to have r cubed over 4. If you subtract those, you get 12q over r cubed. 1/3 minus 1/4 is 1/12. So it's going to be r cubed over 12. Well, those divide out, and those divide out. And all we have left is q, just the charge itself. Woo! So it was right. Okay, so that was part A. Woo, that was fun. For part B, they say show an electric field in the region little r is greater than big R is identical to that produced by a point charge, capital Q, at r equals 0. Well, we already did. If you go outside the region, I mean, if we know that this whole spherical doohickey that we built, if this whole spherical doohickey, if we know that its total charge is Q, that's no different than a point charge of capital Q. So we're going to get the exact same thing as long as we're a distance greater than capital R away. And again, we could do Gauss's law to prove that too. Again, E dot dA equals Q. I'm just going to write it right in there. Or Quank, sorry. I just wrote it in there. Which is E. Remember, it's spherically symmetrical, so it's going to be 4 pi r squared equals capital Q over epsilon naught. That's the electric field's just going to simplify to Q over 4 pi epsilon naught r squared. Okay. And that's just the kq over r squared that we're all used to. Okay. And it's the same thing as the point charge. There's no difference. Part C asks us to obtain an expression for the electric field in the region r is smaller than capital R. So we're going to go on the inside and find the electric field. Now that sounds terrible, but we've actually done a lot of the work for it already. Okay. And I'm going to write it up here. Let's start with Gauss's law. Integral of E dot dA equals Quank over epsilon naught. And again, it's going to be, it's still spherically symmetric, so it's still E times 4 pi r squared equals, and our expression is going to be the same as it was before. It's going to be the integral from 0 to r, because we got to set the limits, of rho naught 1 minus r over r times 4 pi r squared dr. Let me write that over here. Okay. So we got to still integrate all this stuff together, and all of it's divided by epsilon naught. Okay. But because of the last problem, we've done almost all of that part before. Okay. We went back and we integrated everything, and I'm going to actually take the results that we had from the first time we did it. Just rewind like about 4 minutes or 5 minutes. You can in this video, and you'll find it again. I'm going to take from right before we substituted in the limits from 0 to capital R and just replace them with 0 or 0 to small r. So the left side we didn't have before. It's still e times 4 pi r squared. And this is going to be 12 q over, I'm going to put epsilon naught with it this time because we didn't have that before, capital R cubed. And it's going to be little r, that's little r cubed over 3 minus r the fourth over 4r. Okay. I mean, really, essentially, that is the answer. Okay. But they don't, but the answer that I give you in the key is actually different looking than that. So first thing, so to make it look like that, we're just going to move everything over slightly. Okay. First, we're going to divide out, first I'm going to multiply everything times 12. Like this 12 here, I'm going to distribute to all the terms on the right hand side. So it's going to be q over epsilon naught capital R cubed. This becomes 4 r cubed minus, actually let's divide out. No, it's not r the fourth, 3 r the fourth over 4r. Okay. That is e times 4 pi r squared. Okay. I'm going to divide out an r squared from every term. Okay. So that means this becomes, and I'm going to divide the 4 pi to the bottom also. So this is going to be e equals q over 4 pi epsilon naught r cubed. And this thing becomes r minus 3r squared over 4. Okay. And the answer that is in the key just factors out an r from both those terms. So it's qr over 4 pi epsilon naught r cubed, and this is just or no, there's a 4 here too, I didn't bring down. 4 minus 3r over 4. Okay, or no, it's over r, isn't it? That's capital R, and that's a capital R. Sorry about the weird edit there, but I accidentally clicked on the pause button. So in any case, so now it is the answer that appears in the key. All right, well again, work through that, go back through it in your own notes, probably neater. And if you have any, and again, that's a hard question to do. So good luck with it.